Our next rule is the quotient exponents rule. So when we multiply, or are taking the product of exponents, we add their numerators. When we're dividing, we're going to subtract. Now, why does this work? If I had 2 to the 5th over 2 cubed, that means I have 2 times 2 times 2 times 2 times 2 in my numerator and 2 times 2 times 2 in my denominator. This 2 is going to cancel, so is this one and this one. That leaves me with 2 2's. So my answer would be 2 squared. Well, 5 minus 3 is 2. So that's why this rule works. So for example 1, if I have a to the m over a to the n, that becomes a to the m minus n. Remember that all of our variables are just standing in for real numbers, in this case integers, so we can go ahead and subtract them like this. If I have 3 to the 7th over 3 squared, that becomes 3 to the 7 minus 2, which is 3 to the 5th. If I have k to the 7th over k to the 12th, I still subtract them. That gives me k to the negative 5th, and what do I do with negative exponents? I put them in the denominator. Now, I'm trying to make that look more like an exponent. Now, when I have 2 to the 7th over 2 to the negative 3rd, my suggestion would be use the quotient rule before you use the negative integer exponent rule, because you'll see it's going to cancel out. If I have 2 to the 7 minus, because we're always subtracting, negative 3, that gives me 2 to the 10, right? And if I had decided to take 2 to the 3rd and move that to my numerator, I'd have 2 to the 7th times 2 to the 3rd, which is 2 to the 10th. So either way would get you the correct answer. I just like using the quotient rule first. So here is the second power rule, and it says that if a is any real number and r and s are integers, then a to the r raised to the s is going to be when we need to multiply those powers together, i.e., a power raised to another power is the base raised to the product of the powers. Let me do an example. If I have 2 cubed squared, that means I'm asking me to take 2 cubed times itself twice, right? That's what it means to square something. That'd give me 2 to the 6th. 3 plus 3 is 6, but 2 times 3 is also 6. So we want to go ahead and multiply them together. So in example 1, I have a to the m raised to the n power. That's going to give me a to the m n. In example 2, I have ab to the m power. It's important to note that I have to take a to the m and b to the m. I can also distribute that m over fractions, as in example 3. That gives me a to the m over b to the m. Now, why does this work? Well, let's say I had 2 thirds squared. That would mean I'd take 2 thirds times 2 thirds, and we would multiply the numerators and multiply the denominators, right? So it does distribute across fractions. For example 4, I have p to the 8 raised to the 3rd power. That gives me p to the 8 times 3, which is 24. For example 5, I have 6p to the 7 squared. Remember, I need to distribute that. So I have 6 squared p to the 7 times 2. I'm going to simplify that to 36 p to the 14th. Now, I simplified it to 36 because I knew what 36 was. If I'm given something that I don't know what it is off the top of the bat, feel free to leave it in exponent form, right? Don't feel like you have to pull out your calculator. You only need to replace it if you want to, or if the homework problem asks you to, or if you already know the answer. I knew 6 squared was 36, but 6 to the 7th, no idea. I'd have to get out a calculator. Next, I have a over b to the negative n, so I'm going to get a to the negative n over b to the negative n. And when we have negative exponents in the numerator and the denominator, we know the denominator has to go to the numerator, and the numerator has to go to the denominator. So that would be our final answer. So when is an exponential expression fully simplified? An exponential expression is fully simplified when each base occurs only once, there are no parentheses, no powers are raised to other powers, and there's no negative and no zero exponents. So remember, if I have something to a zero exponent, it becomes 1. Next, we need to talk about scientific notation. Scientific notation uses exponents with a base of 10 to represent all real numbers, actually. So a number is in scientific notation if it's written as the product of a number between 1 and 10, and the number has the form n, where n is that number between 1 and 10, and r is an integer. So for example, if I have 376,000, what I can do is I can take my decimal point and move it over 1, 2, 3, 4, 5. I did that because then I have 3.76, which is a number between 1 and 10. I could then take 3.76 times 10 to the 5th. This is another example of a mathematical shortcut, right? Much as exponents save us time not having to write repeated multiplication, scientific notation can be really good for writing really big numbers and really small numbers. Now in this example, that's not entirely apparent, but what if I had 9, 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? If I was writing a scientific paper or doing my homework and I had to write this number over and over and over again, I'm likely to make an error, and it's just really long. This would be 9.123, and how many times would I have to move the decimal over? Let's find out. Well, I would have to move the decimal over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, right? So 9.13 times 123 times 10 to the 12th seems like a lot less work to write. So that's when scientific notation can be the most helpful. So let's go ahead and write these numbers in scientific notation. First off, I have 601. I'm going to take my decimal place and move it over 1, 2. That gives me 6.01, because I need a number between 1 and 10, times 10 to the 2nd. Next, I have 12,325. I'm going to put my decimal place right there and move it over 1, 2, 3, 4 decimal places. That means my answer is going to be 1.2325 times 10 to the 4th. You raise it to the power of the number of spaces you move the decimal over. So let's expand this. If I have 2.49 times 10 to the 3rd, in order to undo this scientific notation, instead of moving my decimal place to the left, I'm going to move it to the right. So I go 1, 2, 3. And any place there's a blank, I'm just going to fill in a 0. So this would be 2,490. If I have 3.52 times 10 to the 5th, that's 3.52. I move my decimal place over 1, 2, 3, 4, 5 times. Fill that in with zeros. So I have 352,000. One thing is, we don't always have whole numbers, right? These are whole numbers. Sometimes we have fractions which are represented as decimals, right? So this is when we would use scientific notation with negative exponents. Remember, negative exponents represent a fraction. So for example, if I had 10 to the negative 1, that's 1/10, which I could write as a decimal as 0.1. If I have 10 to the negative 2, that's 1 over 10 squared, which is 1/100th, which I could write as 0.01, right? So this is where we get our tens place, hundreds place, okay? So I can write in scientific notation with negative exponents by, instead of moving my decimal place to the left, I move it to the right. So here I go, 1, 2, 3. That gives me 4.52 times 10 to the negative 3rd. So let's go ahead and expand these two scientific notation numbers in scientific notation with negative exponents. So I have 3.52, and I need to move my decimal place over 1, 2, 3, 4, 5. That gives me 0.0000352. For our second example, I have 2.49 times 10 to the negative 3. So I'm going to move my decimal place to the left, 1, 2, 3. So now I have 0.00249. Let's go ahead and write these last two examples in scientific notation. So I move my decimal place 1, 2, 3, 4 to the right in order to get a number between 1 and 10. So that's 5.67 times 10 to the negative 4th. For this last example, I move my decimal place over 1, 2. That gives me 1.56 times 10 to the negative 2.